Thanks everyone for joining us today. This is a world first. World first today to celebrate the December event, which is carrying on at the moment in education of science and technology, engineering, and math. We're going to bring you something unique that I believe, or as far as I know, has not been done anywhere in the world. A live exoplanet where a star on the other side of the universe is going to wink at you for the next 2 hours. And so I'd just like to welcome everyone. We've got a fantastic panel lined up today. And I'm going to go firstly to Scott Lewis, who you may know from the virtual star parties, and who's my trainer here. And I'm almost off my training wheels on Google Plus Hangouts. So over to you, Scott.
You're doing fantastic, Peter. Hi everyone, I'm Scott Lewis. I'm also known as the Bald Astronomer on Twitter. I work in the Education and Public Outreach Division of CosmoQuest, where we find ways of bringing science to everyone across the world through citizen science. I'm also the broadcast producer for all of our shows, including the virtual star parties, where we're able to connect telescopes up to cameras in the Google Plus Hangout and share it from across the world. And Peter is one of our wonderful astronomers, and again, here is Shah, who is another one of our astronomers we've had the opportunity of working with. Why don't you introduce yourself, Shah?
All right. Hello, guys. Good morning, or is it night over there? My name is Shahrin Ahmed, and call me Shah. I'm from Kuala Lumpur, Malaysia. And I've been doing around astronomy for quite some time, and recently I've been doing solar images from here in Kuala Lumpur. We don't have very great nights over here, so I switched the time zone to daytime. And it's been great having been able to join you guys in the Hangout for this time. Hopefully we get some interesting news about Qatar-1b.
And it is the Asian century, so there was a very special guest today. Now, Shah has a special filter on his telescope that no one else has. It's called the smog of Asian cities, and he does a fantastic job pumping out great astro images through the night skies in Bangkok and across. He travels around Asia a little bit. So recently, visited Australia for the eclipse. Yeah, so back to you, Scott.
Wonderful. And the biggest reason why we are here, though we do all love astronomy and looking up at the night sky, the big event that's happening this month, so the month of December, we've been dubbing it the month of December. And joining us with us is Tamara Hudgens, who is the Executive Director of Girl Start. And if you could introduce yourself and let us all know about all the amazing things you guys are doing.
Well, hi everyone, and we're just thrilled. I mean, I'm hanging out with you from my house in Walberg, Texas, which actually is a fantastic place to look at stars. We have a small telescope set up here, and we have absolutely no interruptions in our night sky. So we're thrilled to be part of this. And actually, my daughter and I, who are on the Hangout, we've been looking online a little bit about exoplanet transits. So we're really excited to participate in this virtual star party. Girl Start is dedicated to STEM education for girls. We do after-school programs and summer camp programs, year-round programs in STEM education that benefit girls in Central Texas. And we are doing some of our programs outside of Texas as well. And we launched December last year as a way to identify activities and fun things for kids to do with their families during school breaks. And so what we wanted to do was to have an activity a day that parents and kids could do together, regardless of gender or age. And so this is an opportunity because December 2012 is presented by Girl Start and Google Science Fair. Google Science Fair has been doing amazing work to bring all of you partners to December to help us complement the activities that we're doing online with these amazing Hangouts. So you can check out, if you have kids or if you know people who have kids, you can check out an activity a day. Today was about chromatography. And we'll also have these Hangouts available as well through our website. So we're just thrilled that you're here. Thank you.
We're glad to be here. It's a lot of fun to be engaged, and just raising awareness for the STEM fields, and I think it's very important. Regardless of where you are on this planet and who you are on this planet, we should all be able to embrace this and be able to be curious and discover where it takes us. So I'm going to hand it over to Peter real quick to give us a quick overview of what we'll be looking at tonight, because it's some big words of exoplanets, extrasolar planet transits, but what does that mean, and what are we going to be doing?
Okay, so firstly, a little bit about the setup here. This is my telescope, which is a 0.5 meter plane wave telescope with a beautiful camera, a Finger Lakes camera, which is a very high-end camera, and a 12-position filter wheel. It's based in New Mexico. So what we're going to be doing tonight is using this telescope. We're actually logged onto it right now, and I'm going to show you the live images coming in from it in a minute. The beauty of this telescope is it's hosted at a very dark sky site. So, so even though it's broad daylight here in Australia, which is handy for classroom time at school, we're actually, it's just gone, it's about 2 hours after sunset in New Mexico, and tonight, because of the good time zone across the US, we're able to get a transit that was right up against the astronomical twilight, and we've got about 7 or 8 data points that have come in already, so we'll be showing you those in a minute. So. And then what we're going to do is plot a light curve. Now, what is a light curve? That's probably a good question. So a light curve is where we measure the brightness of stars. Now, this particular star is going to have a planet come across in front of the star. So if I can pretend I'm Pamela Gay for a moment and get a couple of little visual things here. Right? So here's the planet. It's a K-class star with a high metallic content, and we're going to have this little, it's hopefully not square, but there are diamond planets out there now. It's going to come across, let me do this so that it works right. It's going to come across in front of the star and block out some of the light. So this is like a mosquito flying in front of a headlight, or a fly flying in front of a headlight, or something like that. So I think this star is about a 12 magnitude star, 12.8 magnitude, and this planet is 1.1 times the size of Jupiter. So it's going to pass across in front of the star, and the light is going to dim ever so slightly. Now, one of the interesting things about exoplanets is that you can actually see them with very small telescopes, because you're actually just looking at the light. And if you have a way of measuring that light with a CCD camera, charge coupled device camera, like we have on this telescope, which is quite sensitive. But even on a little tiny 4-inch reflector, you could put a decent camera on it and be able to do this sort of work. So amateur astronomers for a couple of years now have been really intrigued by this since we started discovering planets around other stars. So let me just show you here what the telescope's currently doing. I think, where's my desktop here? Oh, my desktop.
It's hard being in 2 continents at once, isn't it, Peter?
Yes, that's right. So here we go. This is, I'm not sure if you can see that okay. Actually, no, I need to share it, don't I? Hang on. Screen share. That desk, select that. There we go. So here we've got, this is the portal. Now, my telescope is part of the iTelescope network, which is a group of people who own telescopes who affiliate themselves with iTelescope, and we share them out. And people have a monthly subscription account and log in and use them across the world. Now, as you can see here, we've got the right ascension and declination here, which is where the star is in the sky, and you can see it's 41 degrees above the horizon, which is pretty good. And you can see we're already 39 images into the run. Now, what happens here is that every image is taken, we're using R filter, which is the red end of the band. Stars have lots of hydrogen in them. For photometry, we often use V band, but for exoplanet work, we like to use R band for that. As you can see here, the telescope's up and running, it's doing its thing. So what happens from the telescope is we then go across to an application called VFOT. Now, people in amateur astronomy who do real science quite often are members of the AAVSO, which is the American Association of Variable Star Observers. So the AAVSO is a body of amateurs and professional astronomers who have got a lot more data there than what I was expecting to have. Today would be good. I don't want last week's data. A bunch of amateurs and astronomers from around the world who've created a data repository of all the variable stars. Now, they have some wonderful tools which we're going to be using today, and one of them is called VFOT. So, as you can see here, this is universal time. So you can see these images. These are the first 9 images off the telescope have already come in. So I'm just going to select those 9 images here and show you what we do with them. What we do in virtual star astronomy, and I use this technique for exoplanets as well because it's quite good, is you're looking at the brightness of a star and you're comparing it with known stars around it, and then you just do a mathematical arrangement of how what the brightness is of that star. So you can see here, what we do is we create a sequence. I should show you that first. But anyway, let's just have a look at the time series here. Just takes a little while to come through. Just the server might be a bit slow.
And while it's loading up for Peter, what I'll just mention here for you is I have a way of I will be viewing any comments that are coming in through either Twitter using the hashtag December, also on the event page, or any shares of the Google Plus Hangout that goes out. I will be able to see any comments that are coming in. So if you have any comments or questions for Peter and his setup, or what exactly we'll be looking at, feel free to make them, and I'll be responding to them here on air as we're doing, as well as on YouTube.com. So if you go to YouTube, make comments there, I'll be able to see those comments, and I will manage them and get them on over to Peter so we can help answer your questions on what's going on here. It's really easy to think of astronomy as just looking up and enjoying the heavens, which we all have the ability of doing. What Peter's doing here is called photometry, which is studying the light that's going on, which involves a lot of data coming in on his CCD chip, and we're able to measure the light that comes in to know if something's passing in front of it or something's acting a little wonky that we weren't expecting. A little later on in the Hangout, what we'll do is we'll show you what this data is actually meaning is happening. And I have my program of Celestia up right in here, so we're looking at the Earth. But I'll be able to show you what exactly is happening when we're seeing this data change. I have a visual representation that we'll be able to see this exact star, Qatar-1b, or Qatar-1 with its exoplanet, Qatar-1b.
Cool. Sure. Something's just happened to the to my web page there. Oh, here it comes. Yeah, it's back. All right. Just went off to do something. Oh, yeah, it was just uploading some more data for me. That was good. So that's good. So you can see here we've got the first 15 images. Now, I was a little bit late getting started, but so what I'm going to do here is just highlight the first 4 images and show you what we. I think the transit's going to cut in fairly early because it was very close to the astronomical twilight. So here we're going to do a time series, and we select a sequence. Now, what is a sequence? A sequence is where we have we're looking at the target and we're comparing it with the stars around the target. All right. So there we go. We're already. So as you can see, this is quite interesting. So. Usually when you're doing a light curve, there will be errors in the signal, and it will bounce around quite a bit. So as you can understand, when you're taking photos of the night sky, every single one of them is different. Shahrin can tell you all about that. And there's what we call errors. So if we're comparing one star with another, or three others, and then we're assuming, or we're calculating from the point spread function of the star in the photo. I'll show you the actual photo in a minute. We actually get a fair bit of jumping around of the star. But as you go on tonight, you'll see that this light curve will actually adopt a pretty good shape, and then we'll find the ingress point and the egress point. But the ingress point is going to be quite close to the start of our run. Now, it's not ideal because we usually like to get about half an hour's data beforehand, and I had it set to auto start tonight, and because I was already logged onto the telescope, it didn't do it, and I had to manually start it about 10 minutes late. So, but that's okay. So let me show you the image here. This is the last image that's come down off the telescope, and now what you'll see here is that this one is actually inversed. So what we've actually got here is a photo where the sky background is white and the stars are black. That's just what we call a reverse of the histogram. The other thing you'll see here is that the stars are actually out of focus. Now I'm going to show you why that is in a minute. Because what we do when we do very particular exoplanet transit work, what we do is we take the photos out of focus quite deliberately, and this is about 1,400 steps out of focus, and I'll show you why. Because I can show the ADU readings here. You getting this, Scott? Does that look all right?
Yep, I'm seeing everything there, yeah.
So this is our target here. Now, the reason why it's a little bit out of focus is that what we try to do is spread the light over more pixels, right, so that we can get a better mathematical calculation with lower errors, if that makes sense. Now, as you can see, this is still fairly light because this is a 30-second image. We're taking 30-second images of each of the star here. What we don't want is one of these pixels to get to 65,000 and overexpose and spill over into the other pixels around, because that introduces extra noise to the signal, right? So what we're trying to do here is keep all these ones as average as we can and fairly flat. And you'll see here that the point, what we call the point spread function here, is fairly flat. It's not really pointy and coming down sharply. So we deliberately take these photos out of focus so that we can get a better mathematical calculation on what we call the signal to noise ratio. Now the signal is anything inside the annulus here, which, if you have a look back here, is this little green ring inside here. Every light photon that hits the camera within that is called the signal, and then everything that the sky background calculation in the sky annulus here is called the noise, or the sky background. So we're actually taking a signal to noise ratio, and as you'll see here, we've got quite a strong signal to noise ratio of 226, which is really good. Anything above 100 is really good. So I might hand it back to you, Scott, for a minute, just to talk about your display there while I crunch a few more numbers here, and hopefully this is coming through for everyone and you're enjoying the broadcast. So thanks.
Not a problem, Peter. Thank you very much. So as we're seeing here, he has an inverted image because it's much easier for them to see the contrast if you're having a bland white sky as opposed to with the black dots, as opposed to what we typically see if we're looking up at the night sky and see little twinkles of light. Now, over here, I have this amazing open source program called Celestia. You can actually get it for free at home and are able to take your own tour of the solar system. So as you can see here, I'm zeroed in on our Earth, and it's nice and pretty. and we can take a three-dimensional representation of where it's at. All these lines in the background, which are blue, are just the other orbits of the star. So when we're talking extrasolar planets, well, we can first need to realize what sol means, and we're talking about our sun. That's literally the name that we have for our star, which is Sol. So we're going here to our sun, and we can see that it's just one star amidst billions of stars throughout the universe. And we happen to be fortunate to be amongst many other planets within our solar system. So our first planet that's really close to the sun is going to be the planet Mercury, which has actually had some great discoveries within the last couple of weeks as far as with the ice and organics on the North Pole. So we're able to take a look at our solar system. And so the planets that we've always known about have been, well, up until Pluto, which has been demoted, but we still love Pluto anyway. But we've always been familiar with these planets. Now, this term extrasolar is something fairly new because we haven't been able to really know about them. We haven't had the technology to discover planets outside of our own solar system. The closest star to us is 4 light years away, so the light coming from there, it takes 4 years for that light to reach us. So we need very, very precise instruments and a really good way of knowing how to detect these, and then a very particular way for the planet to move in front of that star. Now, I've seen a couple comments coming in about how far away the star is, Qatar-1, and it's 550 light years away from us. So it's relatively close on the universal scale, but the light that we're measuring right now, the light that Peter's gathering with this telescope, has traveled across the universe 550 years, and he's catching this light. So Peter wasn't alive, and none of us were alive when the light left. We're just catching it when our ancestors were alive. And so it gives you a way of imagining how big the universe is, and this is just something within our own galaxy. So I'm going to bring us back to Earth, our lovely home, and we're going to be able to do something quite amazing with this program. So we can take a look at how pretty our planet is, but we can do also something, another thing that's really great is we can take a look at this specific star. So if you can see this little red reticule right there, that's where that star is. It's really, really faint. Can't really see it with the naked eye, but we can go here with the magic of the internet and the software. So we're going to travel through our Milky Way galaxy and reach this star, Qatar-1. And then as we can see, there's this lone planet floating around it. And this planet, like you said, like Peter mentioned, it's a little bit larger than Jupiter, and Jupiter is the largest planet of our solar system. And it's actually larger than every other planet made in our solar system. So if you took all the mass of all the planets, Jupiter would still have more mass than that one. Now, what Peter's actually measuring now with the photometry, studying the light and talking about the magnitudes, is that we can measure the amount of light coming from the star and reaching the computer chip, reaching the sensor on his camera. And what's actually happening is I'm going to speed up time just a little bit and make it go the right way. And as you can see there, the planet itself is crossing the sun. Or not the sun. It's not our sun. It's a star. So it's, and I'm going back in time once more.
That is cool.
And so we'll make it go just a little bit slower this time so we can actually see what's happening. So we see this light, and actually, let me zoom in. We see the light coming through, and we can measure how much light's coming from that star. And when we're talking about that star winking at us, we're actually noticing the fact that less of that light is reaching our detectors, reaching the telescope. So when we're having that change in light coming through, something's got to be happening, whether it be atmosphere, whether it be something else. And so when we're detecting extrasolar planets, we need to be very precise, like Peter's doing, and weeding out different errors and watching the light come in and actually drop down. We're seeing we're receiving many photons less than what we were doing before. And this planet is actually going around super, super fast. I'm trying to remember the orbital period of this, but it's really quick. I believe it's 34 days. Is that right, Peter?
No, I think it's even shorter than that. Actually, I shouldn't probably speak because I've been working on a couple, and I'll make sure that I've got this one. I think its period's only like a day or two.
It is, yeah. I just pulled up the data.
You can actually get it 3 nights in a row and then miss it for 4 nights and then it comes back again. So one of the reasons why we're studying this one is because it actually has timings, variations in its transit timing. So we'll talk about that a little bit later. But yeah, I think it's about 1.3 days off the top of my head, but don't hold me to that.
I just pulled up that data, and it's 34 hours. So when we think of a year for us, we think 365 days. That's our orbital period. For this planet, it goes around its star every 34 hours. So I'm not too sure about its rotation as far as what its days are, but could you imagine you having birthdays every 34 hours? I really don't know as far as being on a gas planet like Jupiter, but I wouldn't want to feel that old. I don't know about you guys, but I really wouldn't want to feel that old. I feel old enough as it is.
Yeah, so that's great. So are we all ready to hold our breath?
Let's hold our breath.
Let's hold our breath and let's go. Now, I did have the other one up on screen, so I'm just going to swap back here and go back to my screen. So here we go, folks. Drum roll, please. Sorry, it helps if you pick the right buttons, doesn't it? Going to select, not the first one, we're going to select all of them. So we've got 33 data points. So the transit today is going to be, we'll have about 150 images by the time we're finished. Now, on the telescope, we're a little bit ahead of where this is because it takes a few minutes to upload to the VFOT server, which the AAVSO run as one of their tools. So any AAVSO member can use that. So here we go. Time series. So what it does is it takes those 33 images now. We select the sequence, which is, remember, the target identified and the comparison stars and the check stars that we're using around that target. And we're going to start the analysis on the curve. And we'll see what we should see, fingers crossed, we should see the light starting to dip. Now, here you can see, now remember I said before that when we started it was almost right on the ingress. So you can see here the first 3 data points that we've got are a little bit higher than everything else and it's dropping down. Now what we'll see tonight is more accentuated on the egress when it's coming out than when it's going in. But you can actually see here.
I'm not seeing anything on your screen, Peter.
Oh, okay, let me just try and reshare that again. You got that?
I'm just seeing your list.
Well,
there we go. That's better.
You got it?
Yep.
Okay, so as you can see here...
Could you zoom in a little bit to your graph?
Yeah, I'll try and zoom in a little bit. You zoom in. Now, there's very subtle differences here, and the importance of what I mentioned before is that getting the half-hour data beforehand would have been better because we would have seen a lot more data up here around 0.03. Now, the magnitude here is just the relative magnitude between a couple of check stars around it. But you can see here how we've got, some variation. There's a variation in every process. And you see here how it's starting to decline. And then once it goes through that, it'll bounce around, but you'll see none of these high points will be above any of these ones here. And when we actually reduce this data and get the full 150 data points of the curve, you'll see this a bit more pronounced because there'll be a broader spread. And when we come out the other side, you'll see that it'll come across and come up sharply as well. We'll have a better, it looks like we only got about 5 or 6 data points before the ingress. But what the key telltale here is you can see all these ones are heading down. and then it's established. So it looks like the the instrumental magnitude here was about 0.28, and now it's declined as it's gone across the limb of the planet, and now it's stabilized down here at 0.01 at average, right? So as we go through this, you'll see this will get a more significant picture, and it will stand out to you more as we go. All right, so there you go. It looks like we've got the ingress there, and that's quite exciting. So
that is quite exciting.
Yeah.
Now, I'm getting a couple comments from people saying that they're not able to see all the screens when they're moving around. So just want to make sure that
probably
that's being clicked on.
Yeah. So just an answer to that question, in the Hangout, the screens are voice activated, except for the person who owns the Hangout, who might have been quite distracted by trying to crunch some data there, and that's why I highlighted the screen for your zoom in on the exoplanet there before I got that one. So I'll put you back to the. So do you want to? So transit timings. This is interesting. So I might go back to my camera for a bit so I can talk. So Scott, one of the things with the transit, perhaps we could just go back to your image graphic again and just slow it down and just have it, and I'll just talk through what we're actually seeing here. So so what happens is that, so we know roughly how far this star is away, and we know what class of star it is, so we generally have a bit of a size. Now, the first thing is the period of the exoplanet, so how often it comes in front of the star. Now, as it comes in front of the star, what you see is not all of the planet is eclipsing the star at the ingress, which is about now, as you can see there. Right. You see there's just a little bit. So that's where we're at now. We're a little bit further along than this, but in our light curve, you'll see how now this is quite important because astronomers like to get the ramp of the decline of the light. So as the star is partially across, the planet is partially across in front of the star, the light starts to drop. And then once it's fully in front of the star, then we have an idea about, then the light's going to be constant until it goes across the other side and comes out the other side. So if that makes sense. So what we're looking at is a line that's kind of like a, if I get my finger in the camera, it'll come across and it'll be constant, then it'll go down and it'll go across and then come up and then out again. So it's just like a little, wedge-shaped in the. So it's quite important that the shape of the ramp down and how long it's at its eclipse state. So because that gives us some critical information, how big this planet is. So the length and the steepness of the ramp. Obviously, if it's a very steep and it just drops suddenly, obviously it's a fairly small planet in compared to the star. But if it's got a shallow drop and it goes down slowly, then obviously the planet is a bigger planet because it's taking longer to cross the limb during the transit. Does that make sense?
Absolutely. Yep.
So then if you can sort of fast forward a little bit. Where we were in the light curve is we're about where it's just, I think, fully inside. So probably the telescope is now about halfway through. The data that we've uploaded is probably just a little bit past here. So if we can go in a little bit further. So I think what I just showed you then was about this much data. Okay. So the telescope's running probably about half an hour ahead of us, and then when we come out the other side, you'll see it ramp up. So this is really, really exciting to be bringing this to you today. I'm quite excited how this has turned out. It's really good.
Now, Shah, have you done any exoplanet research or observing there from your observatory?
Well, no, exactly, because we usually have transits every day on the sun from the clouds.
Yes.
So we couldn't really didn't really do any yeah. So this is great because by looking at Peter doing the telescope halfway around the world and being able to get all the data coming in, so it's great. It's wonderful. I mean, just to imagine that we can't do this a couple of years back and we can do it now. So it's great.
Right. It's just amazing that we're able to literally see new worlds we've never been able to imagine. Yeah, it's been great. We've been able to catalog new star systems, but now we're actually able to detect full planets, and these planets are tiny. When we're thinking about on this large galactic scale, they're so small. Every speck that you see out into the night sky is a star within our own Milky Way. And if you look hard enough, you might be able to see another galaxy. But these are huge balls of fusing hydrogen and helium. And just like our sun, they're all over the place. And our planets are so tiny. So if you want to put the focus back onto Celestia real quick, what I'll do is I'll give you a bit of a scale for us to see. So we're going to go back home. We're going to go back to our sun. And so here we are. This is our sun, and we can zoom out and go further and further and see the orbit of Mercury, and then we have Venus and Earth, Mars. There's this big gap, and then we have Jupiter and Saturn, Uranus, and Neptune. So here we have the furthest out technical planet that we have. And then we have things even further out in our Kuiper belt and the Oort cloud that surrounds our star. And we're looking at the star, and even looking at its scale, this program is actually scaled up. It's really big, and you can't even see the planet. All the planets themselves are just tiny little specks. You can kind of see Jupiter because it is the biggest mount, so we can, if I go and click on Jupiter real quick, I'll center on it. We'll travel in. This is the biggest part of our solar system besides the sun. And the planet we're looking at is Qatar-1b is larger than this. And the reason why we're able to catch that data is because you have something larger blocking the light coming through. And so being able to detect another planet from 550 light years away is mind-blowing. We've never been able to do this ever before. It's very new within the late 20th century into the 21st century. So it's extremely exciting that we can find other worlds that might be similar to our own and find out what goes on with planetary evolution in these other places within our own galaxy. I don't believe we'll ever have the technology to look at planets in another galaxy, but at least for our own neighborhood, I think that's a good start to go on.
There's one interesting question on the stream, Google stream, by Nathan Matthews. He was asking whether Earth would be detectable from the same distance using the same process that we are doing now, since it is much smaller and has a longer period. So is it possible for Earth to be able to detect on this distance?
Yeah, well, if they had a space telescope like Kepler, yeah.
Because what we're looking at now is we're dealing with the angular resolution that we're able to do with the telescope and the sensitivity of the camera. So if we're able to put this out into space, we're put the hardware into space, we don't have to deal with anything from the atmosphere messing with the light coming down, because we have an atmosphere, we can breathe, living is a good thing. However, when it comes to gathering light on a telescope, the photons do interact with the molecules within our atmosphere, so it does cause problems for astronomers. So they get into this love-hate relationship with living and doing astronomy, or having money in your pocketbook, because that gets expensive too. But I think it might be possible, but I don't think it's anything that any of the amateur level might have. I know that JPL does do some exoplanet research up at the Mount Wilson Observatory with the 100-inch telescope, which is enormous. What is the size of your telescope, Peter?
Yeah, so it's a 0.5, a half meter, so 20
So a half
inch,
meter.
yeah. So well, I can pick up a hot Jupiter. To give you some scale here, and coming back to the question that was asked, this is about a 20 millimagnitude transit, right? So 20 thousandths of a magnitude. Now I can go down to about, I think, 13 before it all goes to noise on my telescope, but the Kepler Space Telescope can go down to 4 10,000ths, right now, of a magnitude. Now, as you know, and forgive me if any Kepler people are watching, I'm doing that from memory, so I'm pretty sure that's roughly about its scale, because it's outside the Earth's atmosphere, and they've got very sensitive, obviously, higher end cameras again, so what the Kepler Space Telescope can do, and its primary mission, in fact, is to look for Earth-sized planets, because in the Drake equation, you have, how many planets are likely to have life on them. And there's all these variables on there. There's about 27 different variables, and one of which is the number of Earth-sized planets that might be in any solar system or galaxy. So the purpose of, or I guess part of the broader purpose of the Kepler mission is to calculate the number of Earth-sized planets that are out there. Now, to answer the question that was asked, you could not see an Earth-sized planet with my telescope. You just could not do it. It's too small, because Earth, is I think about 1/300th the size of Jupiter. So we need the Kepler Space Telescope sitting out there in space without the atmosphere blocking its view to actually get the down to the tens of thousands of magnitude to pick up an Earth-sized planet. Now, they've already discovered or picked out signals that need to be confirmed, but they've already picked out signals for, I think, about 200 likely Earth-sized planets, which is quite exciting. So hopefully that answers the question, Shahar.
Yeah.
So yes, if someone on Qatar-1b was looking at our sun and they had a Kepler Space Telescope, they could potentially see us. But they wouldn't see all our industrialization just yet, because
true.
We've only been making radio noise for about 50 to 70 years. So anyone who is out there planning to come here is operating off a very good business case. They're doing it on no observable data that there's supposedly intelligent life here.
Well, that's still up for debate in some places. So.
True.
So as your data,
Tamara's there. So maybe if I could pitch a few questions to Tamara, given that this is December, and that science, technology, engineering, and math is the the STEM curriculum in the United States, which everyone's talking about. As an educator and someone tied up with this, what does what you're seeing here today mean to you as an educator and someone inspiring young women in science?
Well, one of the things that we do ask questions about, and we are part of the NASA CP4S-MP+, which is an informal science program. We're continually asking questions about the ways that we can make physics so that we can understand more about the universe really understandable. As you know, so much of this, and there was a hangout yesterday with CERN about how we understand things about the universe, and it seems to me, boils down to very complex math, which can seem very intimidating. And at the same time, you end up working in these mathematical areas all day long. Are there any tips or any strategies that you've used in order to embrace math even more, I guess is one of our questions. We love math, of course, but not everyone does.
Yeah, the scary math particularly.
Well, I think that's something I get to work with a lot when I'm doing, I instruct planetary astronomy at the college here, and I get many, many students that were raised with the idea that math is hard. They don't know math is hard, but they've been told that math is hard, and so it's automatically ingrained that it's hard, and it's hard breaking somebody out of that. So one of the tactics I try to use in the class is to use visual aids. I use Celestia on the big screen projector. I let them see what we're talking about, and I try to have them visualize. Unfortunately or fortunately, we have a great amount of technology, but we're also born right in front of this technology, and having to use our imagination has become a little more difficult, I've noticed. So giving some visual cues and allowing them to, in their mind, go to this other star and this planet 550 light years away, and then I can talk about Kepler's laws and what it actually means with Kepler's laws. And I think tying in the visual component with the idea of a physical law, so a law of physics, how they look, and then, okay, well, this is just a simple equation that we deal with. So I introduce the math at the very end, so they know how it works, they know why we're looking at it, and now it's at least at the level I'm doing, it's a fairly simple equation that they have to work out. But once they start seeing those patterns in it, hopefully it's not too terrifying. They have their final on Monday, so we'll see how really terrified they are. But I found that if we can introduce different layers of the same concept, I find that helps a little bit more, especially with students that are terrified of math for no other reason than it's been told that it's terrifying. Because I think with anything, if you're told to be scared, you're going to be scared.
And we deal with this type of issue related to perception all the time. And so we don't think that math is challenging at all, but it, again, is this thing that somehow is ingrained that, hey, math is hard, but of course it's not. I'm curious, actually, also, with your experience, I was just looking at Celestia. Can Celestia be used with a projector?
I use it onto the projection screen inside the lecture hall. So I have it just output to the other one, and there it goes. Typically when I'm in a hangout environment, you're seeing me through my laptop with my webcam, and so I have a standalone machine just for this. But I use this, and also there's another piece of wonderful software called Stellarium, and I use that during our virtual star parties, which will be on Sunday night, where you have I believe, Shah, did you have that up earlier, or were you using a different software?
I was using the Sky Safari, something similar like similar like Stellarium. Yeah.
Right. And what I really love about Stellarium is, again, it's an open source piece of software, so it's constantly being added in from the community, but it's also installable on Windows, Mac, and Linux. So to whatever environment you're running on with your computer, you can run them. And I find it absolutely wonderful. You can learn the night sky. You can actually get cultural influences as well, so you can see what the different cultures thought of the different constellations throughout the world. So what we might think of as the zodiac here in the Western world, we don't have a unique view. Everybody has their own concept of what these objects were, and it's really interesting looking at humans through astronomy, because it's not always a way of looking back down at Earth, but it is definitely a human endeavor to look out into space and be curious about what's out there.
Wow. Yeah, this Stellarium looks amazing, actually. We're in the process of considering whether we can build a mini planetarium at Girl Start in the beginning of the next year. So this could be a great resource. Yeah, we have a star lab that we use in schools, but Girl Start's building is a former nursing home, and so the headroom on the ceilings is very low, and so we can't use our star lab at Girl Start, so we have to take it to schools, which is important. But this Stellarium could easily be used in that dome space. So I'll put it out there. If there's anybody out there who's built a dome, please let us know how you did it.
Very carefully, I'm sure.
Absolutely.
And if anyone out there, I'll put the links out into the event page as well of where I got these software. Again, it's community-based, it's community-driven. The one is Celestia, the other one is Stellarium, and it allows you to, Celestia here lets you explore not only the solar system but our galaxies in 3 dimensions, and then Stellarium lets you look up and have your own observatory from where you are. You can move your location to me here in the Los Angeles area, or I could set it up to be where Shah is in Malaysia, and it's great. You can look at a night sky you've never seen before. Yeah, I've never been to Australia where Peter's at, but I can look and see what's going on with software, but then thanks to Google Plus and the Hangouts, Peter can literally show me what's up in his night sky that I've never been able to see.
Yes,
That's
exactly.
incredible.
Yeah, because when I was in Australia during the eclipse last 2 weeks, and I was talking with the astronomers over there, and I told them, "Look, Orion is upside down." So they said, "No, it's not upside down."
Absolutely, it's and the moon's upside down, and what's going on? Because you grow up realizing that the sky looks a certain way, and okay, the Earth is a sphere. For anyone out there that thinks it's not, we can show you literally to the star parties that the Earth is a sphere just by everything looking upside down compared to where we're at. So one thing debunked tonight. All right. But yeah, I love the fact that we can share, with you, Shah, and Peter, and we have Ahmet in Turkey, and Umair in Pakistan, and throughout the UK and Denmark, we can all get together and share our universe just from a different perspective. Yeah. Another thing I think you would like tomorrow as well, we'll actually be going into a little bit more detail on our Tuesday broadcast, but let me pop this window open to here, see if that popped up. CosmoQuest is where I work for. We do citizen science, and our first one that we put out was moon mappers. So what you can do, and anyone can actually do scientific research from their home in their fuzzy bunny slippers if they choose, and you can mark craters. We have the highest resolution images since the moon landing from the Lunar Reconnaissance Orbiter, and you can go through and mark the different craters here, and you can take a look as far as where the sun is, so you should know which way the shadow's facing. You can mark different features through, and on Tuesday we'll be having a hangout with the NASA Dawn team about our other citizen science on Vesta, but this allows all age groups, regardless of where you are on the planet, you make an actual contribution to the to scientific research. We're publishing the data from it. We already did one in August at NASA Ames. We delivered a paper there, and we'll be putting out some more research at the American Astronomical Society's conference in January. So this might be something too that would help with your Girls at Girls Start to. They can do astronomy. Yeah. They have the means to understand what's going on, and they can become mappers, and they can do cartography of a different body, which I think is awesome.
Well, one thing that we did in our Girls in STEM conference in March of 2012, and I'm sorry if there's a jingling of a dog scratching herself over there, but all of the girls at Girls in STEM at the end of March, because NASA is working on, among, of course, other things, figuring out ways to land on an asteroid. Mm-hmm. And so we had 500 girls design their own asteroid landers, because, of course, awesome. NASA needs to figure out how to land on an asteroid in order to mine that asteroid for those precious materials that are there.
That's one thing I love, is that
really
there are
great
so many
to have
projects.
Girls, now, wait a minute, why do I want to land on an asteroid? Oh yes, some of the pictures are interesting, but yes, we'll absolutely share them. We were initially encouraged to think about it like a competition, and we said, well, it would be more fun for everybody to collaborate and to share ideas and not worry about the competition part. And so as a result, we had 528 girls, each developing her own asteroid lander. So, and once they found out the purpose or the reason for landing on an asteroid, which most lay people would say, why would you ever want to land on an asteroid?
Because you can.
And of course, how
because
would
you can.
Well, yes. And I think the other question is, well, doesn't that involve, of course, a lot of math? But once girls realized, hey, the motivation for landing on an asteroid is that there are materials that you can't find on Earth, or if you find them on Earth, they're so scarce that actually it's worth the effort to build something, to shoot into space, to actually land on an asteroid, to mine those materials and to bring it back. And as we find with all of our programs, when you make STEM relevant for girls, they are ready to take on that challenge. And so that's why another reason why it's great to participate in these hangouts. So this is a lot of fun.
No, absolutely. And I think getting that curiosity, I think, is very important, is making it personal to them. No matter who you are, if you have a personal emotional investment in something, you have that motivating factor. Then all of a sudden you realize you're learning math that you never thought you'd ever learn just because you want to understand this. And I'm sorry, everyone, but math and science is the language of the universe. To better understand what's out there, you have to speak it. And it can be an uphill battle. Well, once you do, you start seeing the universe in such an intimate light that you wouldn't be able to understand beforehand. And I think it's something that's mind-blowing to me. Is it literally is a language, and you can start speaking and knowing how things are working that you wouldn't have been able to comprehend beforehand.
Yeah, no, I think, Tamara, one of the key things for me, as a person who wasn't good at maths in high school and really struggled, I had to do the subject twice at my Associate Diploma of Engineering when I learned how to multiply sine waves together and do Fourier transforms. That was really scary, but I got through it, so I'm not the world's greatest mathematician, but look at all the stuff you can do today. It's quite amazing, and I think from my point of view that the key thing about math is that you understand what it's for, and I think quite often, with teaching methods perhaps of 20 or 30 years ago, it might have been a little more blander than what it actually is now when you look at something like the Khan Academy or all the great work you do with STEM, in terms of teaching people what math is for and capturing that vision as you just described. And then you can go through the stuff. It's like anything, you want to be successful at anything, you've got to push through the pain. And not that maths is painful, but and some people, there are personality types that are more adept to it, I guess, than others. But it doesn't mean we shouldn't, work hard at it. So.
Well, and it's really amazing. Again, once you just say, you know what, if you they're just numbers. And when you use these numbers, you can predict where planets outside of your solar system are going to be. That is an extremely powerful and compelling reason to absolutely embrace math, because you're able to do things that your parents wouldn't have been able to do, that your grandparents weren't able to do, that very few people are actually able to do. Girls will be highly motivated by that.
Oh,
Anyone
absolutely.
would be highly motivated by that. Yeah.
I think a lot of it is, again, in the perception and the delivery of math as a subject, from a very young age. And it's very hard to switch gears into actually learning what maths are. And I remember growing up, I always just remember that question in the back of my head, and I know everyone said, why do I need to know this? Why do I need to know this? And I think, and something I try to incorporate with my classes, I like giving them the reason beforehand and then the how. So here's the why. This is what we're trying to do, and this is why we're trying to do it. And this is the math that allows you to. So you can use this as a tool. And it's a little bit slower, but it allows them to appreciate it and not be terrified when the next time you have to approach math again. Is that, oh, okay, I know what I have to use this for something. It's not just random knowledge you'll never ever use again. Most people think, oh, I'll never use algebra when they're in high school. And you're using algebra all the time. You're just not thinking about it in algebra. When you're counting things, those things are variables, and then all of a sudden you're just using real-life algebra, not thinking about an equation per se, but you're using algebra all the time, and that's just the basis of when we're getting into trigonometry and then into calculus. You need to be able to understand that, and having that connection of I do this all the time, I just don't think I'm doing it all the time, having that aha moment of it's not hard, it's balancing my checkbook. Well, that might be hard for some people, but it's very simple, and seeing that connection on the application, then the math, it becomes relevant again, and now you're not too terrified, or even if you are terrified, there's actually a purpose behind it.
Yeah.
So I'm looking through the comments here, and Chris, I believe it's Dutka asked, I'm sorry if I mispronounced your name, Chris, but he's wondering, what does the star actually look like in the CCD right now? So are you able to pull up a live image and take a look at what's going on?
So we've had the server, the telescope's just taken a little pause in uploading the data, so it's still crunching away. Here, where are we? Where's it gone? I restarted the browser there. So anyway, we've got 33 images that were uploaded, and so let's just have a look at the last one. Now it's actually up to about number 80, I think, from memory. So it'll keep coming through. I think it should be nearly out of the transit. Was supposed to be out by it was a 92-minute transit, so we should be nearly out by now. But it'll take a little bit longer for the data to come through.
Okay.
So that's what it looks like when it presents to VFOT. Now that's not the question you asked. You actually want to have a look at it directly through.
Well, you're not sharing your screen right now.
Oh, okay. Sorry.
We're looking at you, which is fine.
So look,
you're a good-looking man, Peter.
I'll just download a photo directly off the telescope for you, and I'll show you an image of that. Just so let's talk. What else do we got to talk about? Any other questions? While I'll go and chase that one up for you.
Oh, and actually, I had a question too regarding your telescope. Do you have any images that you've done with typical astrophotography that you do on a normal basis? Can we see the power of your telescope in the optical sense as opposed to photometry?
Yeah, we could probably have a go at that. There's quite a. In fact, I won't probably bore you with my work. I'll give you. I've got one here from. Hang on, let me. Just give me a sec. Yeah, there's a beautiful, stunning image of M81 and M82, which has been done by Jeff Woods, who spent a whole night sitting out in the freezing cold, doing a polar alignment on it. So he got some time to take. He uses the telescope quite frequently and took some. Where's my preview screen going? Lost my preview. Oh, here it is. Preview. Where's my preview? Oh, here we go. Preview. I'll pull up that image for you and I'll just show that to you. So we've got any other questions while we're doing that?
Let's see. I had actually a great comment here from Craig. Craig Wilford makes a comment saying, "This is amazing. I'm so glad to be alive at a time when I can experience something like this with you all. We're watching a guy control a telescope on the other side of a planet to show us a planet move in front of a star that is 500 light years away. I might not have my jetpack yet, but this is the future that I was promised as a young child." And I think that's absolutely right. We're able to do so much now, and it's so easy to take it for granted. I have a smartphone that uses Einstein's theory of relativity to map where I'm going when I'm in the car, and we're able to do so much now. My smartphone, for instance, is much better than my first computer. So it would put my first computer to shame and would destroy it. But we have these things that fit into our pockets. So I completely agree with you, Craig. This is the future that we were promised, and it might not be the Jetsons yet, but we are having driverless cars start hitting the road here soon, so that's always exciting.
All right, so here it is. You ready for this? This is quite an extraordinary image. This is a 4-image mosaic. So for a camera like mine, I think it's a 12 megapixel camera. So it's 4008 by 2675 pixels. And this image is actually 4 panes in a mosaic to bring M81 and M82 together into one image.
Oh, wow.
I think it's I think probably the original photo of this is some gigabytes in size before it's recropped and scaled down for an image you can put on a website. So it's quite stunning. So Jeff Woods, who is an exceptional astrophotographer, this is M81 on the left and M82 on the right. You can actually see the colours, the red, lanes in that. It's quite good. So, I, as an amateur astronomer, spend probably more time doing variable stars and this kind of work on exoplanets than I do doing the pretty photos, because there are a lot of techniques, and I'm sure people are saying, well, how the hell do you take a photo like that? Well, you actually take a lot of images in the red, green, and blue channels separately, and then you integrate them together using a software package like MaximDL, or there's a number of others. And then once you have it in RGB format, you then can pump it across into something like Photoshop, and then play with the levels and the curves and the gains and that, and you can achieve quite good results. And at iTelescope, we've got an introductory package where people can sign up for a free account and take 4 or 5 different photos just on an all-color camera, which is quite simple to use, just as an introductory tinker with the system to try and get the feel for it. And then if you want to get more involved, well, then there's a lot more you can do. It's itelescope.net.
Well, and I want to give a little context to your image, because it undoubtedly is absolutely gorgeous. And what we're looking at here is M81 and M82, which doesn't really mean much to most people, but these are other galaxies. Now, when we're thinking galaxy, we're talking about our sun is one of so many stars within a galaxy. So we're just a tiny little speck inside of a spiral arm of the Milky Way galaxy. Now, M81, it's also called Bode's galaxy. It's 12 million light years away from us. So the star we're going over, Qatar-1, is 500 light years away, which is a long time, or excuse me, a long distance. Now, we're looking at something here that's 12 million light years away. That means the distance that light traveled took 12 million years for that light to be here. And it's absolutely just amazing on the detail you're able to get. And you're able to look literally into the past. You're able to see what was happening in the universe 12 million years ago. And the further back you look into the universe, the further you're actually seeing back in time. So to be able to see complete galaxies and seeing 2 of them in one image, it's just trying to think about that and give that sense of spatial analysis in your mind is crazy. And we're able to do this now. I love the fact that along the lines of human enlightenment, we're decided to go into optics and have been able to do some amazing things with understanding on how we get better angular resolution with images and be able to see entire galaxies where we wouldn't be able to see them before.
Yeah, I would like to add on that on Scott's comment just now, because what do I have here is a screenshot over here. This is actually what we can see with the naked eye currently from New Mexico. It's where the Qatar-1b is located, somewhere near Draco, I think, if I'm not mistaken.
Mm-hmm. Yeah.
So this is what we can see, or we can't see with the naked eye, because the star is basically very dim. I think it's about magnitude 12, I think, if I'm not mistaken. So we need to have optical telescopes to be able to see the lights coming from that star, which is like 500 light years away. But with the naked eye, it's just an empty space over here. You can't see, we can't really see anything over here. But just to imagine that there are something over there, and now we can actually see it with the aid of the optical telescope. So it's great, just to think about it.
No, absolutely, Shah. It's stuff that you literally can't look up and see, but we can use tools and we can understand the physics behind things and manipulate it just right to where we can see the photons that traveled for 12 million years, and the photon that hits your eye, no one else gets to see. So you could literally see something that no one else is able to see. Now, thankfully, there's many, many, many photons out there. There's a lot of energy that we can observe, but it's just profound. And when we're able to do these things, whether it be with Qatar, where we're looking at another galaxy, it blows us away that we're able to do this and understand our universe in a way that we would never have thought possible through typical means.
Yes.
Now, I see a comment here on YouTube that was relating to Tamara and our conversation here about math, and they're asking, who is teaching students that math is hard, and at what age do they believe this? It can't be girls it can't be just girls that end up believing that, and they're absolutely right. It's not a gender thing. It is for everyone. I would never assume that boys are more adept at math. I actually know many brilliant women I work with that blow me away in mathematics all the time. So what do you think, Tamara? What do you think that age that it starts being ingrained in them that math is hard, and who do you think's doing that?
Well, firstly, Girl Start is founded on the general principle that girls, and I'll just preface this because I realize that we're speaking to an international or with an international audience. And so I'll say that girls in American educational environments, particularly between the 4th and 8th grade, which is approximately 9 to approximately 14 or 15, there's a precipitous decline in interest on the part of these girls in STEM topics, electives, and career pursuits. And this is not just math. It is also science. It is everything in that STEM acronym. But we do see that students of both genders do have this problem where they are receiving messages from the general community that math is somehow hard. And I believe that it isn't just I would say the popular culture or the popular community, but there are a variety of messages that we as people in the world, we send, as parents, we inadvertently send, and as people in the world, we generally impart the idea that math is hard. And I think that for all of us, if we realize that the messages that we send as people, as aunts and uncles, as parents, as teachers, as practitioners in the world, if we stopped saying, you know what, I'm so bad at math, that would probably do quite a bit to help, this general thinking. But there is something interesting, particularly with math as a topic, that across the board, you will find people that have negative experiences to it. And we don't like to take too much time to take potshots at those that might be considered to be the agents of that. What we like to do is we do informal science, which makes all of the STEM acronym fun. And so what we try to do is we try to combat that malaise wherever it comes from or from whatever it originates, and to make all of the STEM acronym fun. And we believe that through informal science, it can be combated. We're seeing that informal science is not just for the out-of-school time zone. It is also a great technique for engaging students during the school day as well. So through our Distember.org website, which has a ton of activities, through our blogs about our Girl Start After School and our Girl Start Summer Camp program, that's at least some of the resources that are available. But there's a boatload of amazing science and STEM organizations that also have informal activities that you as a parent or you as as a teacher, or you as the person in the world, you can have fun with STEM with kids, and that's really the first step.
Right. Now, I know one thing that got me hooked as a child, and I've seen it happen multiple times, is that first moment looking through a telescope and seeing Saturn and its rings. It's something I will never forget. I will always remember for the rest of my life that we hear about Saturn. We see cute pictures of it in a book. But that first time you see Saturn and you see the rings and you see the shadow of the planet on the rings, or even the rings' shadow on the planet, it's a real place now. It's not this fantasy land that we're always told stories when we're kids, but I can see it, and I can go back and see it again, and I want to see other things. Just you don't even have to turn it into a huge science lesson. Just let them just be blown away and shocked and awed about the fact that I can look at another world, and the way that I've only seen pictures of it. I think that's something that's profound, that whenever we have local star parties, we get a lot of people just blown away. Children, young and old children. So you can be a child when you're 88, and people have never seen it before, taking the time to look up and be able to see something that they haven't considered before.
And Scott, when you lead with wonder, and this is something that I actually think is one thing that Girl Start is trying to do. It may not be a stated intent, but we lead with wonder. We lead with that open-ended, hands-on question. Hey, what do you think? How would you solve this? And, in your case, with regard to seeing Saturn, it's like, okay, you've seen this amazing thing. How do you get there? How do you find another one? I mean, just, questions like that. And that's one of the things that we find, that some people who aren't maybe, more in the formal environment, it takes the joy out.
Right.
And when you lead with wonder and you lead with wondrous questions, then you can continue the joy. And that's what we find continues to happen at Girl Start as well. And I realize, again, if you go to our website, you'll see that our website and all of our activities are wrapped in pink and fun and lots of exciting graphics. But we don't think that there's anything incompatible with fun and scientific rigor. I mean, we're doing real science. It just happens to be, through candy chromatography or testing static electricity by using PVC pipes or what have you. So we absolutely embrace that, because we think, just like you, that if you lead with wonder, then wonder will continue to follow.
Oh, absolutely. That's one of the things that the students I work with were blown away by, was that, like, wait, you have fun? Like, oh, you have no idea. And most people think of scientists as being in a dungeon lab or in a cold observatory on a mountain, or having beakers and test tubes and Bunsen burners. And I will be the first to break this, saying, scientists party. We have a lot of fun. We make lots of jokes. We have a good time, because what we're studying, we have passion behind it, and we are very excited about what we're doing. But we also, at least the majority of us, the vast majority of us, do know how to go and unwind and have a good time, and are allowed to enjoy it, and enjoy not only what we do but its implications. And we love getting other people excited about it. I know for me personally, being able to excite somebody in the same thing that excites me when looking up at space and looking into the night sky, that does it for me every time. I know I'm doing something awesome if I can share that wonder that I have. That way I don't feel so alone in the idea that science really isn't looked at, at least in our society, as this great thing to do anymore. Most people want to be sports stars or celebrities, and I'm not one of those. So when I can find someone else that wants to get into this and be just as excited about the amazing universe we live in and our place in it, that gets me every time. And then, yeah, we'll go out for a beer afterwards, and it'll be all right. So.
Well, and you've also just hit it on the head. That's one thing that we do in all our program is connect science activities with a profession or a career, because girls don't know, okay, they can do a science activity, but if they don't see themselves doing that in their life and see themselves, okay, I am this person, this is the kind of life I can have, it's really hard for them to see how they can make that personal journey from engaging in a science activity to being that type of science practitioner. And that's why these hangouts are so fantastic, because those in the audience that are participating, you can see these are real life scientists. They're hanging out on Google+. Yes. And it's fabulous that you all are participating, because I mean, I'm learning a ton. I'm certain that everyone is learning a ton too. So this is thrilling.
I think it's great, and we love being able to participate in this, and we do this for free. This is not something we're getting paid to do. We do it just because it's fun for us. It might be a little stressful at times getting things set up, but while we're here, we have a blast. And I'm involved in at least one per week, typically more, but we get together and we share what we love. One of the hangouts coming out tomorrow is with the women in STEM on Google+, and they're with Erin and Bedini and I believe and Rajani Rao, and they're talking about monkeys. Now, I'm not a biologist, but monkeys are awesome. I have my space monkey right here, and this is physics monkey actually. But we actually get to look at something that I don't get to go and actually look at. I believe they're Diana monkeys, and they're in the Ivory Coast. But it's something that we have this ability to look into the lives of people we wouldn't typically be able to see. I don't work with biologists all that much, except for in passing. So if we can actually see research that's being done in Africa, why not? It's better than watching a documentary. We get to talk and we get to have a conversation about what's going on. Yes, I'm an astronomer, but there's other things that are out there that are very interesting to everyone. And I love the idea of December, that we can look at all the different fields. We can have a conversation with these wonderful research scientists and find out what gets them up in the morning, what really excites them, and what have they discovered that we haven't known about before. I think that's fantastic.
Yeah. Well, and you've also hit on something that is really important, and that is that we all generally feel like consumers of technology or consumers of data, rather than creators or authors or shapers or curators of this data. And that is one thing that's also really vital about these Hangouts, is that it shows this audience that there are real people doing this work, and everyone has the opportunity. I mean, through that Moon Mappers, I'm blown away by the Moon Mappers, and I'm certain we'll have a conversation at Girl Start about it next week, because any opportunity that we can take to have girls, or anyone, be an author or be a creator of data, or an interpreter of data, that is a way to stop the passive engagement and make it active engagement, which is far more effective. And really, as we know with the national or international STEM deficit, that's what everybody needs. We need more people to be engaged in this work. And so that's another reason why December is, I mean, we're so thrilled that it's fun for everyone as it is for us, because we think that by highlighting something like STEM during the month of December, if we can get more people excited about STEM, and then they can head into Google Science Fair, into January, and think about really amazing science fair projects, we can continue this cycle of, hey, wait, science is fun.
It is fun. Absolutely.
Look, Scott, I just thought I might just show you something else for a minute. So we're not stalling on the Exoplanet here. This is all really great conversation about education and science. And that was definitely part of the plan today. We're just waiting for a bit more data to download to the server before I can update you on the light curve, and I'm not sure, there's a few interesting things going on there. So with the server, so I'm just waiting for that in the background. But how do we know when these transits are going to occur? I think Pamela pinged me the other day and said, I so love the phrase that you have booked an exoplanet transit, and we should acknowledge Fraser and Pamela, who are the marvellous educators and outreachers who taught us how to do all this crazy stuff. So the answer to that question is on the Tresca database. So I'm just going to let me just screen share my desktop desktop with you, and I'll show you. This is a tool. Now, there was a very famous amateur astronomer who had a bit of a cult following called Bruce Gary, and Bruce had a Exoplanet database that he ran. You see that now?
Yeah. I'm seeing your entire desktop right now.
Yeah, cool. All right.
There you go.
So here, and this is called the Tresca database. Now, the database that Bruce Gary worked very hard on coordinating with amateurs for many years got handed over to the Czechoslovakian Astronomy Society, and they run it as one of their services to the community. So in here, you can tell where the longitude and latitude of your telescope is, and you type that in. The longitude is not east or west, it's sort of 360 degrees subtracted from where you are, so that it actually comes to a whole kind of number. And then we can see here Qatar-1b. So on this is universal time at 1:46 a.m. 8th of the 12th. Which
Peter,
was
not to interrupt you real quick, but I believe your screen's still on me in the Hangout.
okay.
To show the people. I mean, I'm enjoying it, but I want them to actually see too.
Okay. Sorry. Oh, is it what you're saying? Put it up on that one, yeah.
Let me see if it's
sorry.
popping up here.
Let
I'm just a slight delay on the video.
Yeah. You got that?
I am seeing infinity. You're sharing your desktop instead of the...
Yeah, hey, actually, yeah, that's probably what, yeah. Let me just correct that.
It looks fine on me, so...
I should just screen share the browser, not the, yeah, this one, I think, yeah. So,
in a way, this is very interesting because you can actually see the astronomers at work, the stressful face.
Yeah,
trying to get everything worked out. So it's great.
It's so stressful. No, we want everyone to have a good experience. So,
but he's also a pampered astronomer because he's not out there in the cold.
No, that's right. Soft, very soft.
Because it's getting quite warm down there, isn't it?
Yeah. So here we are in the. This is called the Exoplanet Transit Database. Sorry about that. So here we are, and Qatar-1b, you can see here, started. The ingress began at 1:46, and the center of the transit was at 2:35 Universal Time. So we take off 7 hours for New Mexico time. That was 6:46. And it should be out by 8:46 by that. So we should probably be finished now, but we're still waiting. Part of the problem with all this cloud-based services and remote astronomy is it does take a little while for the files to upload. So I'm just going to check here and see if we've had an update. Let's just see. So what do we got here? Oh, we got 62. All right, that's great. That was so. This should be about at this point almost through to the coming towards the egress, I think, because it was only 92 minutes. So if we have a look at the timestamp here, we've got 2:36 Universal Time, and we said the egress. So this is right up till the start of the egress now. So and these files are coming through half an hour delayed. So we should have another download very quickly now, and we should be able to see the egress, hopefully. So let's have a look at this now. Keep getting that on the screen. Yes, we are. Good. I love this. This is so exciting. 12B. Here we go. Start the analysis. Now, sorry, that would be the wrong one. That's the one I did 2 nights ago. We want Qatar-1, not WASP 12B. So there we go. So, you know, this is quite exciting, and, you know, what gets me really excited about Australia. So this should show you some interesting stuff. So as you can see here,
There we go.
Nice.
The results page, and we'll go through. Now, I'll just comment on a few things here, and I might just zoom in a little bit here. Zoom in. This is so good. So what we're looking at here is the signal to noise ratio of our star. Right now, as you can see, the signal to noise ratio varies, but hopefully it varies by the same amount in our check and comparison stars as well. As you can see here, what we've got here is that because it's setting in the west, the air mass, now the air mass is what we call the thickness of the atmosphere. So if you look straight up, the atmosphere is thinner than if you look out at an angle at the horizon, because you're looking at it at an angle. So astronomers, this introduces extra noise, and that's why the signal to noise ratio of all our stars is gradually dropping here. But what you can see is that the signal to noise ratio of our check stars here, the red one in this one, I think you can see that, is constant. You see how it's going right along that line at 0.6 there, which is the instrumental magnitude. And you can see how our comp stars, even though the air mass is going up and the signal to noise ratio are going down, the comp stars here are very steady. But what you see here is that our target, which is in blue, has been above that line for a bit, and then it's gradually dipped in and it's sitting right on the line. Right? So you can see it definitely has faded compared with our check stars and our comparison stars. So are you ready for it? Here it comes. Here it comes. This is our transit, right? So here we've got the up to about 0.574 here is the pre-ingress. Then you see how it's sloping down from about 0.574 through to about 0.586, and now you can see it's flat across the bottom. And you can see it's definitely fainter here than it was when we first started in the first 8 or 10 data points. Right? Now, as I said at the start, I prefer to have an extra half hour before, but this was right up against the astronomical twilight. So there is your transit. Now, what we're waiting for now, in a few minutes, is it coming out the other side, and you'll see it'll actually start brightening again. So I think we could tick the box and say we've had a success tonight.
I think so.
I'm very excited. So if you can bear with, I know it's a long broadcast, we'll be going for an hour and a half, but if you can bear with us for another 10 or 15 minutes, I think the data will have uploaded to the server, and we'll have the egress as well. So I'll just hand it back to you, Scott, for a minute while I just check on that.
Now Peter's used a couple terms here, though. I want to clarify with him and with you as well.
Yeah,
so we've used one thing. It's called ingress and egress. And what we're really talking about here are two terms about it going. It's starting in, so ingress, and then when it's leaving, egress. So right now, if I go, if you want to put
put
the
big
image
one
back
up.
on me,
I'll
go and.
So that's the ingress, and then the egress.
And now I'm going through space again. So
and he's gone up to it.
Wrong shortcut key. Let me go back there real quick.
Oh, this is so good.
I was just kidding with you all. But
I'm very impressed with what you've done with this diagram, by the way. It's great.
Let's see here. So there's Qatar-1b going around, and I think I'm at 1,000 times of what. 1,000 times 4 times, so we're going pretty fast. I just used the wrong shortcuts because I'm used to Stellarium. Alright, so let me get there. So this is going to be ingress right now. When the planet's coming along and it just touches the orb of the star, when it's entering in, that's going to be ingress. Now, as we go across, I'm going to speed up time just a little bit more. As it's leaving,
so
there, that's going to be egress.
So that's the bottom of the trough, and just as it starts to kick up again, and the ramp, the steepness of that ramp is how wide that planet is with reference to its parent star. and then as we come out the other side, then the star will brighten again. So, so yeah, we're nearly there, I think. So I'm just going to have a look here. Now, if I go back to what we should be looking for here, and I might just quickly grab screen share again. Here, if I show you, if I click on Qatar-1b here, I'll just pop that up. Sorry, why did that not work? Screen share. That one selected window. All right. So apologies to the guy who asked the question before about getting a real image. I couldn't actually download the real image directly, so so this is what it would look like if you had the black background. But here, these are again all the predicted transits for the next 365 days. And if we go back, this here is one I ran last week. So this is what we're looking for, and this is what the processed data looks like. So you can see here, I think we got that up on screen. Yep. So what we're actually looking for is the flat start, and again this was a bit shorter here than when we started, and then the dip, and then across the bottom and out the other side. And so this is what we're looking for. Now this one was the one I uploaded last week, so we should have our egress data shortly, hopefully. Let's just have a look how the upload's going. Processing queue. Oh, yeah, there's all the images. We might have some more. Let's just have a look. And a refresh. We need about 80 images and we should be there.
So as we saw there with that little dip going down, we can actually see right here on my screen that it's measuring the amount of light hitting that detector. So obviously right now when the planet is in front of the star, less light is being received on the detector chip. There's something in the way. Just as if you put your hand up towards the sun to block it, you're having less light hitting your face. So this is the same thing that's happening, and we're detecting that dip in the amount of photons that it's able to be detected on his camera chip, the CCD, and then when it comes back up, that's after the planet's left. That's after it's done the egress out of the orb of that star.
So let's just have a look. There's a couple more images just come through, so let's just have a look and see how we're going here. This is a real leap of faith today because you've got no idea how much can possibly go wrong. And it's worked flawlessly, so yeah, it's doing good.
So Scott, so basically the transit that we are looking now is like similar like the solar eclipse when the moon passes in front of the sun.
Absolutely, or I'm sure some of you might have been there when we did the transit of Venus. So our local planet, Venus, went across the orb of the sun, and we had an amazing time. Was great. I got to go down to just north of Mexico and use a solar telescope in a hangout environment just like this.
Yeah.
And we watched the planet Venus go across the sun. This is the exact same thing,
yes,
but way far away. Now, thinking about this as well, we have different angles we're able to see things at, right? And so we know it's not going to happen again for Venus until 2017, or no, 2117.
Yeah.
So it's a long time because just the angles don't get there right. Now something far away, we have to get those things perfectly aligned to be able to see this tiny planet go in front of this tinier star 550 light years away. So the ability to be able to see this, it just happens to be that they're close enough to a straight line that they're there. There's possibly way more planets out there, but using this method of detection is not possible because they're not at the right angles for us to see them transit across. So just imagine that, we can see a lot. We've detected many, I think it's up to 3,000 exoplanets, but we can't detect all of them through conventional means. So we have to find more and more ways of discovering what's out there.
Yeah.
And who knows how many stars have planets. For a long time, we thought many stars didn't have planets, but now we're starting to see that most stars actually do.
Yeah.
Which is an interesting way. We're seeing our way of looking at the universe differently just by having new means, new technology to detect it and to look out and understand it.
Yeah.
Okay, so let's just have a look at this now. Something's going on here behind the scenes a little differently, which is odd. All of a sudden it started calibrating images that it wasn't calibrating before, so I'm not sure why that is, but anyway, we will press on, and I might have to just leave it where we're at. Let's share the select window. Here we go. So here we go. So we're selecting our sequence, and here comes the egress. But I don't think we're going to get all of the egress. So we'll see how we go here. Because something's happened in the way. I think the run has suddenly decided to change part of what it's doing. But anyway, here we go. We'll go to the result page. And as you can see, we now have just starting to come up out of egress here. So you can see these data points. Again, there's a fair bit of variation here, but you can see it's starting to increase as it comes out of egress. You can see how it's heading back up towards our line up here, which is where the average was before the ingress. So you can see we've gone across the top, down the slope, across the bottom, and we're just coming out the other side here now. So that's really exciting stuff to see that live today. Well, first, as I said.
Absolutely. We've made internet history for right now. We'll see what what tomorrow brings.
Yeah. So look, I'll have to. What's happened here? I'll show you what what's happened. Because this is the beauty of online astronomy, right? So, go back to the images here. Normally, these images get calibrated on the telescope before they're uploaded. And last night we took brand new darks and flats, and for some reason, you can see how these first images were actually uncalibrated, and all of a sudden it started calibrating them. So let me just talk to you about what calibration is. Calibration is when you know how when you take a photo you have vignetting in the corner of your images. Well, when you have
Peter, can you click on your screen real quick?
Yeah, sorry. Yeah.
Thanks.
There we go. I'll just go back. When you have darks and flats, what you're doing is you're actually taking a picture of, in this case, a 30-second image, with the shutter closed, so that it's taking a picture of all the noise inside the camera. And then what a flat is really the shape of your telescope. So it takes a 1-second image when you point it at a bright wall, which is an even color. It's just like what video technicians would do with their white balance. Kind of, they take a photo of the white and then they subtract it. So what happens there is, and something's happened to our darks and flats here, and I'll show you exactly what I'm talking about here, is that all of a sudden something's changed here and it's all started calibrating our images. So the result of that is that, and look, I can correct this later because I can use the uncalibrated images, and I'll get all the data together for everyone and we'll post a nice photo. But what actually has happened here, and this shows you the great things you can do with remote astronomy, but also some of the things you've got to watch as a scientist, because what it shows is that because those images are calibrated, it's now changed the sky background. of those images. And so that's changed the signal to noise ratio, which I can correct later in the reduced data, but it'll muck up our graph here in just the uncalibrated way, and I'll show you exactly the difference, right? So it's quite interesting. So what you'll see here is that all of a sudden you've got some images down the bottom here that are different in their instrumental magnitude. And this is actually a good point, because it'll highlight some of the things that we deal with. Right? So because these images are calibrated differently to these ones up here.
You're not screen sharing right now, Peter.
Oh, sorry.
It's all right.
Screen share. Because these images are calibrated differently to the other ones, you can see how the sky background is different. So they've dropped off the cliff. Now that doesn't mean to say the planet's got darker all of a sudden. What it means is that and this shows you how sensitive the technology actually is. What it actually shows you is that the sky background in these images is different. Because if I show you, you see these calibration ones here have been calibrated differently to the rest. So in here you'll see probably not a lot of difference, but when we go back to, actually I can do it this way, it'll show you. Let's see if I can cheat here by using the back button. Yeah, back to summary. Oops, no, it doesn't like the back button. Yeah, we might not do that.
So do you think that after the Hangout's finished, will you be able to
yeah, so I'll tidy up the
put
images.
an image with your average lines, with your mean lines?
So yeah, so I'll do that. I'll have to, because I'll what I can do is re-download the uncalibrated versions and upload those. So that'll be fine. But I mean, let's not fuck around with it too much. We'll go back to here and we'll just take those images out for now, and I'll upload those later. But this is the trials and turmoils, and some little thing needed to upset us today to show just how on the cutting edge we are. So which is great.
Well, sometimes when you're on the cutting edge, you bleed, and that's okay. That's all right. We're, like we were talking earlier, we're doing things that couldn't have been imagined 10 years ago. Who would have thought you've been able to connect with people from across the world, control a telescope from across the world, share the photometry data, and be able to have a visual representation of an exoplanet all at the same time? I'll take a couple technical hiccups along the way. I'm okay with that.
Yeah. So these are the individual frames that I can check, and you can see how the sky background's quite even, and in those last couple they would have been different. So I'll correct that in the final image, and because I have to submit the data anyway, because there's a scientist in Russia waiting for this, so he's going to be surprised that he made the headlines today. So there's our light curve. I think you can see that. Yeah, it's in the window. Yep. So again, you can just see it coming out the egress here, and that's probably a good time for us to wrap up. And I'll post the final image when we got it up on the in the question in the event. So I'll just go back to I'd personally like to thank everyone for joining us today. It's been absolutely brilliant. First live exoplanet transit, and really want to pay tribute to Dr. Pamela Gay and Fraser Kane, who inspire us with all this stuff. They take risks, and we've taken a lot of risks today to do something this crazy and this live, and the weather was kind to us, and the telescope held together, so that was good. And so Scott, I'll hand it back to you and Tamara then for a wrap up, and you can sign off, and we'll finish the broadcast.
Very good. Now, for those of you not aware, Fraser Kane and Pamela Gay are the the ones that co-host the Astronomy Cast. Fraser is the publisher of Universe Today, and Pamela is a professor at Southern Illinois University, Edwardsville, and also from CosmoQuest with myself, so she's my boss. And one of the most amazing women I've ever met in my entire life, and not just woman, she's just the best person I know. They dedicate a lot of their time to education, public outreach, for free. With Astronomy Cast, it's being paid for by donations only. The same thing with CosmoQuest. We're doing a lot of it on public grants and allowing you all to participate in science and get that connection to understanding the universe. Again, my name's Scott Lewis. I am on the Education and Public Outreach team at CosmoQuest, along with many other side projects. And Shah, if you could go ahead and introduce yourself again before we sign off, and then Tamara and I will wrap it up, and everyone can have a good night.
All right. Okay. My name is Shahrin Ahmed. Just call me Shah from Kuala Lumpur, Malaysia. It's been great to be able to join you guys. I've been trying to get online for the virtual star party for the past 3-4 months, and couldn't really get that perfect timing, the perfect weather that I have over here. So I mean, that's the life of being an amateur astronomer. So I have to really live with it. So it's fun anyway. So it's great. I'm an educator. I give talks to the schools over here. So from the input that I have from the hangout over here, it's really, really good that I can actually use that kind of input that you have to the talks that I have over here. So it's been great. Thank you very much.
Very good. And Tamara, we have reached the end of our show.
Yeah.
Anything you'd like to add to the end?
Enjoy the rest of your day, since it's morning for you. And we're going to close our evening of December 7th here in Texas. And just thank everyone for participating. I know that 2 hours online seems like, a lot. But this type of work with these significant findings, I mean, we have found new things. And again, as you lead with wonder, as all of these gentlemen have led with wonder, we're going to be experiencing something new, and we can continue to ask new questions that will then present more significant findings. So we at Girl Start are thrilled that you've dedicated your time towards December, and we're just so thankful to participate. And we're also thankful for Google Science Fair's participation and really all of the partners that have been helping out with December. So if you guys want to, I mean, we're going to be doing another hangout early next week, and there are just a bunch of other activities and fun hangouts to check out. So please do, and thank you.
Absolutely. So a quick plug for some of the other hangouts that are happening here for December. Tomorrow, my friends at STEM Women on Google Plus are having a hangout with Erin Kane discussing her research on primatology with Budini and Rajini. Or excuse me, Rajini. I don't want to mispronounce your name, Rajini. I love you. So they'll be going over the Diana monkeys from Cote d'Ivoire. Also, and you can actually search for these. If you click on events in Google Plus and just search December in the search button, you will pull up anything with the hashtag December that is associated with this month-long event. There is also one that I'm producing behind the scenes will be the Dawn mission, Google Plus. We'll be going over with the NASA Dawn team, which has just left the asteroid Vesta, is now heading on to Ceres. We'll be going over with CosmoQuest and how to use the asteroid mapper, citizen science, and doing a question and answer with people from NASA and what do we mean by these different features and images. So I hope as the month of December goes along that more of you will be able to get engaged and get excited about science in the many different fields that are out there with STEM. So unless there's anything else, Peter, I think we can sign off and wish everyone a good night or day or wherever you are in the world.
Yes, so thanks everyone for joining us, and yeah, just wishing everyone associated with December a great month, and we're glad that we could help you kick it off with something a little bit different today. And yeah, so astronomy is awesome. It's all out there. It's just amazing thing, and the amateur astronomy community work closely with the professional astronomers and all sorts of things, and everyone can be involved, and it's just about if you have that passion for astronomy, you can do it too. So thanks everyone for joining us. Thanks Scott for running behind the scenes, and Shahrin for doing the questions and answers there. And thanks Tamara for joining us and leading the discussion with the girls. So thanks very much, and bid you all good day from Australia. And remember, this is the Asian century, so we're in this with you. So so we'll see you all soon. Thank you. Bye.
No. Bye everyone.
Bye.